For people who just attend, we have some schedule changes. The one speaker, uh, for personal reason, he's not able to kind of present. And we have our friend Ben from Ververica that is able to kind of jump right on this session. His session was supposed to be tomorrow, but thank you for he kind of jump right in and be able to kind of share his cool story about all things related to schema. We have about kind of a minute to go, and Ben, the stage will be yours, and I will probably push myself to the backstage. Okay, Ben, go ahead.
So, hello everyone. Thank you for all coming and listening for this relatively short notice change of schedule. The advantage one time of time zones is I was asked in what looked like the middle of the night, but turned out to be perfect time for me, so I had plenty of time to make sure this actually flowed to time. So without further ado, let me share my screen and we'll continue from there. So, well, thank you for coming and to my talk, which now is spelt correctly. Yes, I do actually know the spelling of Avro, but in my original thing, no, it was spelt wrong. I am now very well aware. Cool. So let's talk about Avro, Arrow, Protobuf, Parquet, and why. So, quick introduction. So some of you will have heard me. I talk a lot and at length, so you may or may not know who I am, but my name is Ben Gamble. These days I go by the technology sommelier. It was originally a bit of a joke because my job mostly entailed telling people about cool stuff in technology and how to pair them together. Occasionally I brought out some cheese to go with it, and the joke stuck and sort of became my moniker online. I've worked in a bit of absolutely everything over the years, from trading software to hiking apps to large-scale online games, and increasingly these days in big data and streaming. Kind of for my sins, I founded two AI/ML apps long ago. One did logistics, one did exercise and running games on Google Glass. I was braver then than I am now. And these days I am the field CTO at Ververica. And by the field CTO, I mean the T stands for talking. I will talk at length about most things technology related. I used to be a CTO of my own org, but as kind of time went by, it's more about meeting people where they are and understanding technology more than building it. So, what is Ververica? Now, some of y'all have heard of us before, but just as a bit of background, we've been around for a while, and we were originally the creators of Apache Flink. And we're all over the world powering all kinds of fun things, like across the industry. Apache Flink is often that last port of call in scale and performance when it comes to data processing. And just as the usual examples, I'm contractually obliged to state we're available on cloud, on-prem, and somewhere in between, and in most places around the world. Just kind of a bit of a taste of where we go, right? We kind of end up being part of all kinds of mission critical workloads all over the world for all kinds of people. Now, I say this because I want to kind of show where we've come from, because a lot of what I'm about to talk about becomes very relevant when we start dealing things. And of course, we do it at very large scales. And once again, it will become relevant why I talk about this, because when you're doing petabytes a day, millions of cores and billions of records, certain things matter, and the shape of the data is often one of the most important things. So I've mentioned Apache Flink and I've mentioned Ververica, but not all of you will know about Flink. And really it comes down on this specific thing, which is a bit between what is right in data and what is right now in data, because Flink lives halfway between the two. And without having the data when it's correct and exactly once and with transactional guarantees, more often than not, you've not done something of value. And if you don't do it right when it's important, you've kind of lost the trick. You might have already built your lovely real-time streaming platform. You've got event data flying around. You've modeled domain events and everything. But unless you can act upon them correctly and when they happen, you may actually have a problem. So let's talk about data. So some history. Some of you will have heard me say this bit before, but fundamentally, we have to kind of go back a bit because I want to get the kind of the handle on scale and change, because change is often the biggest driver of stuff, right? So the first megabyte hard drives existed back in the 50s, right? 1957, first 1 megabyte hard drive. Then we actually got to 1980 and we had the first gigabyte hard drive. So a few years later, we've gone up, 1,000 times in scale. The joke about 640 kilobytes being enough was from 81, or at least it is apocryphally credited to it. Increasingly, the internet is now divided on who said it. It probably wasn't Bill Gates, but at least it's amusing to think it was. Then once again, like a piece about scale. We've gone from in 1980 to 19 years later, the turn of the century, to a gigabyte in RAM. So what was your total disk available to your computer is now the total amount of memory available to your computer in volatile space. And then we get to big data in 2001 and the first terabyte hard drive in 07 and now. Now you can get, terabyte SSD cards. People talk about exabyte engineering when I was at university, and now it's just a thing many organizations have is multiple exabytes of data. But just going to zoom back a little bit. Big data was in 2001, right? It's 24 years later, and it's still a thing and still a challenge. So let's talk about how we use data, because this is actually kind of tells a story about how we manage it and how we kind of do things with it. So at the core of your computer is a CPU cache with registers. Now, this is an untyped amount of bits, and you have tens of bytes worth of bits, nearly always arranged into certain types of cache lines, so you can process a number of bits at once. With things like SIMD, you get extra wide pieces of registry, which means you can process multiple data points at the same time, as long as they're roughly the same sort. Now, at the CPU cache level, types sort of go away. You just have a string of bits, and then you're operating on them. The instruction set you're using at this point doesn't really care. Your assembly might, and this is where you get the idea of higher speed operations are coded in assembly. Like you'll have a bitwise addition of integers across a SIMD cache of 10 integers. That's an optimization. But the actual registers themselves don't care. You can shove anything you like in there and it'll do an integer math calculation on it, and you might get a weird result. When you go down a layer, you get to your RAM, and this is where you get typed structs up into the tens of gigabytes. And the key thing to note here is that I say these are typed because your programming language of choice has decided to lay out your data in a specific format. An integer is an integer at this point, a floating point is a floating point, and each with their own precision numbers, and any kind of complicated compound type is basically some level of layout which has a structure to it. And once again, tens of gigabytes is really the kind of scale of most single things in main memory. When we go down again, we end up with files, and we can have silly numbers of them. Now, I say files with an asterisk because files can mean almost anything. In a Linux operating system, everything is a file, up to and including a port is a file, a socket is a file, everything is a file. When you start dealing with more kind of other kinds of operating systems, particularly Windows, there are other things other than files around, and files mean something specific. Thing I always remember back in the kind of when you start looking into how disks are done is disks are actually laid out in a very specific format. Now, I've worked with everything from raw flash all the way up, and the kind of formats on disk actually matter quite a lot. But for today, we're going to kind of skip a level up from there. Because once you kind of got beyond one machine, you got more. So you had your disks, and then we have multiple machines. So you have more than one computer talking over a wire. Now, the wire is kind of characterized as a bunch of untyped bits in packets. Now, the packets here are either UDP style packets, where you just have a defined size and you're just throwing them over, depending on what your actual max packet size is on your network before it fragments out. Or you have TCP, where the packets are sort of virtual and there's sort of stream going on between two systems, and they're sort of reconstructed at either end. But the key thing here is that your TCP layer and your UDP layer don't really care what you put in them. Most times you do anything on the wire, you're basically blitzing bits on the wire. Now, I'm going to point out that this very thin line between two systems is slow. It is slow by comparison to any of the previous things we've talked about previously. So when you go from disk to main memory, you can get SATA arrays in the 6 gigabits per second. That's pretty quick. When you're dealing with going from memory to CPU, is something called the memory wall, or kind of your North Bridge level saturation, and that goes in the multiple gigabits per second again. Now, these days you have network NICs that can go into the tens of gigabits in theory, but in actuality, this is kind of a thing where the network itself is nearly always doing other things, and you can't really blitz at full rate without very specialist hardware. Now, I also say slow with a kind of asterisk because there are plenty of times when the network is definitely not the slowest thing in your setup. And particularly in the cloud, a lot of your disks are network attached storage, which has advantages, but also it's not really as fast as a local SSD. And it's very important to note when you're building cloud systems of what are you paying for and why. And if your performance matters, you have to make slightly different choices. So now let me tell you a story. Now, the names are protected to protect me because it's me in the story. The exact circumstances I'll allude to as we go along. So let's start with the idea of you having a SaaS platform, right? Now, in this case, it was a SaaS platform I was building, and it's for booking same-day deliveries. And originally, you have a REST API, you have this exposed to the outside world, you have a combination of retail users who are just logging in, saying, I need this parcel delivered from here to there. It's a courier service on our own platform. And then we had other kind of third-party companies saying, right, we have a logistics depot, we need spillover from our vans, come pick up these 20 packages, 300 packages, 1,000 packages, and go out and deliver them. So that's all well and good. But the thing here is that you now have a bunch of these services talking. And if you were like me when I was younger, you'd do something silly, like directly couple your RPCs into your system so RPC comes in, you couple it with an internal service, and you're basically now waiting on that to happen. Now, this is a problem because once you start doing this, if your request per seconds go beyond a certain point, you will completely saturate your system and you'll start declining requests. Now, that doesn't seem like a problem as you now have a fundamental rate limit, but that's not really how data works, because if you saturate any point in your system, you no longer can take requests and then either retry start and you have a thundering herd, even with exponential backup, or you end up with the fact that clients get annoyed and you do not have the availability they require. So classically, you do the usual thing here. You engineer a loosely coupled network with microservices. You have files for storing data, queues and streams between things. This is where you'll probably learn a decent amount about these kind of systems already today. But you have systems between your stuff, meaning that you can then actually decouple these services. And that sounds great. You have stuff on the wire, things on disk once it's hit, and you're acting upon it, and then you send the data back. And then when a client comes back and says, are you ready for me? You'll have the response for them. Problem is that when people start adding data upstream of your kind of queue systems and your workers, you don't necessarily know what's going on. Now, this actually happened where we accepted JSON records, right? And there was a field known as dimension, right? Of volume, right? And one was a thing, the dimension field, right, had this idea of a volume. So it'd be 3 numbers, height, width, depth. Didn't really matter which was, we could deal with that. That wasn't a problem. But the problem was some were shipped as mass, because in certain things, it was just a pallet. And a pallet could just take a mass. And it didn't really matter if it fit on pallet or not. The problem is that these are a different shape of data. And 2 types of JSON which are not equal are fundamentally not equal. And in a lot of cases, serialization got messed up, and particularly deserialization got extra messed up because something wouldn't fit. And then you end up with systems exploding downstream, which were expecting clean data, or worse still, you just made a horrible error and you didn't know what happened. So this is where you end up in the world of where, what failure mode do you want and how do you prevent it? So we kind of want schemas for this. And at the time, I dug into a variety of different options and ended up selecting a few different ones. And over time, it kind of went a bit different. So I'm going to cover the 2 on the right briefly before we dive into the ones on the left. So the first one actually is JSON schema. Now, a JSON schema is just telling you what the JSON should be. It doesn't really do much. And to be very honest, like outside of communication between teams, I believe this is a relatively weak choice, as there's no easy enforcement for it at either end without a lot of additional coding. Now, message pack kind of goes hand in hand with JSON schemas, but it's a binary way to encode data. basically in a self-describing JSON-like format, except it's binary. And flat buffers are like protobufs if they grow up. I will go into them in more detail as we go along. But fundamentally, like, you always end up with a simple fact of, I want to send data around. I want it to be small. I want it to be easily readable, and I want it to be understood at the other end. And I want to be able to deal with changes as they come. So then we start talking about Avro. Now, Avro has been around for a while. Since it kind of came about and then was donated as part of the kind of Hadoopish era of early Apache days back in 2009. And it's kind of one of the most interesting formats out there. Now, it's sort of become the lingua franca of all streaming systems, particularly with the schema registry for Kafka, though Confluent felt they had to add a little extra bit on the end to make it extra special and give you a kind of an ID for it, even though strictly not necessary, as Avro is fully self-describing. It's dynamic, it's untagged, meaning that the schema part of the data can be pulled off separately, and you could easily get to the real data directly, meaning that you increasingly do not need to do certain things. You don't manually assign field IDs, and it is both a file and a wire format. If you look into how data is often actually stored in files like Iceberg for their metadata, all these Avro files. And it's a row-oriented format. Fundamentally, every record and every field in every record exists in one row, and then you have the next one, and then you have the next one, and you have the next one. It's all bit oriented, meaning that if you write an int that can be expressed in 4 bits, it'll be expressed as 4 bits and things like that. So it'll optimize down to the minimum allowed packing for your data type of choice. When you serialize at the other end, one, you do not need to accompany it with a schema because it's already there. 2, you can just process it without code generation or static types or everything else, meaning you can do tons of generic data processing. This is why Avro kind of really took off and one of its kind of key benefits along the road. Now, not to say the kind of thing to say there is we don't really use some of the cool things Avro can do. Like, you don't really need to do much with Avro beyond just say, I'll read that, please. The reason to share the schemas separately is because you want to verify. Now, verification being important is true, but the idea really is that with when the data evolves to Avro, because of the way it's been generated, you can actually use the symbols and field names to basically pull out the data that hasn't changed. So as you add data to an Avro encoded stream of data, you should be able to keep reading from it. This is why it's kind of really popular with tools like Debezium, because schema revolution happens, and Avro, at least in theory, supports this quite well and can resolve it quite cleanly. So that's Avro, kind of like the older standard here. And before this, we have all kinds of magical XML-ish things going on. Now, Protobuf came next. Protobuf was kind of from Google. And fundamentally, it kind of came from a very different mindset, right? So protobufs assume the whole message goes into memory, and it's not particularly large, and it's not particularly deep in hierarchy. They are serialized in whatever way you like, meaning the only way to check equality of 2 protobuf packed messages is to either byte compare them, literally byte for byte, or to fully unpack them and check them. There's no other way to do it. There's no native compression, and if you want to do anything special, you have to actually think about it ahead of time. So protobuf is when you have a schema, right? It's statically typed and schema defined. You write a protobuf schema, and then that protobuf schema turns into code, which does the code generation step happens, and the code generation is the one that defines both writing and reading these things. It is once again a wire and a file format, though protobuf files are a bit less common. I've worked in places where they've become the norm. Long strings of protobufs became kind of the way we stored data for a game. I do not recommend that. It's kind of a mess. Now, it's once again another row-oriented format, but you can put anything you like in it. Now, they're designed to be kind of a happy medium, right? They're not maximally efficient in speed when it comes to serialization and deserialization. They're actually pretty slow on that. There's a bunch of very interesting blogs out right now from some of the people who do Kafka Streams work heavily, that the majority of their whole pipeline is just deserializing and reserializing protobuf. You cannot act on protobuf as an in-memory format at all. Avro, to a certain extent, you can. I wouldn't recommend. But the reason I brought up flat bus previously was they're designed to be an in-memory or in wire format. So every time you use protobufs, you end up with the simple fact that you have to actually use the schema to fully pull out the data. Then you have to act on it, then put it all back into a new one. And as you end up doing this, you can easily make a bunch of extra copies of your data. This doesn't mean protobufs are bad. In fact, because of that true requirement to run the schema at both ends, it's very good for building data contracts. And this is where gRPC kind of almost took off, in my opinion. Protobuf's enforcement of a strong schema guarantee at both ends basically meant that if I wanted to do an RPC, I could guarantee the other side could read it because they ran the same proto file. In theory, once again, it supports evolution, though in my experience, schema evolution is yet another one of those things like statelessness. It's something we would love to have, but in practice is something that's not worth designing in mind for, particularly when you start dealing with all the various streaming systems and you end up with topics of immutable data. It, in my opinion, is never worth mixing a schema. You should always upversion the topic name to match the schema. So if you have schema v1 in your file, in your topic, Kafka, Pulsar, something else, right? And you want to then say, I want to upgrade the schema to have a new layout, new something else, add 10 fields, take away 3. That's great. Make a new topic. And that means that if you roll back to a previous version of code, you can roll back to a previous topic, and it'll all just work out the box. You never have to deal with skipping records or handling things that could otherwise be a poison pill. In theory, both Avro and Protobuf support various levels of evolution in either forward compatibility, backwards compatibility, or both. I would always recommend that you assume it is not compatible backwards or forwards and basically treat the case when you need it as the kind of exception. It is a complete risk to basically assume forward compatibility when there are easy ways to break these things. Fundamentally, a protobuf never really removes actual data types inside it. So if you keep evolving a schema over time, eventually you end up with a very large number of dead fields there, which never go away, meaning your efficiency will always drop over time unless you create a new schema. I have seen this in action. It got messy and we did not know until it was too late. So how about kind of longer term storage? Because like Avro is fine for a row format and so is Protobuf, but generally like you don't want to be storing them around. Like they are, as row-oriented files, they're not really designed for rapid access besides on a kind of key value lookup thing. They don't give you an index or anything else. And this is where Parquet comes from. Now, I'm giving Parquet its own kind of big call out because increasingly everything is an evolution on Parquet. So Parquet came about because of the Dremel paper. So Dremel is basically the internal name of BigQuery. Not 100%, but really Google BigQuery is something called Dremel. The technology behind it is. And in 2012, there was a kind of project between Twitter and Cloudera designed to basically say, hey, we like that idea. There's a lot of cool stuff here. So then let's make Parquet. It became open source by about 2014, was a top level project in 2015. And increasingly things went along in a very good way, and it continues to evolve to date. And I mean ridiculously fast. Like Avro, like by comparison, is really quite stable. And though I've worked with one of the PMCs for Avro for a while, it was one of those things where it was seen as stable enough that getting people to contribute changes just took amount of time because the community was quite happy with what Avro could do. Parquet, on the other hand, has increasingly become the default de facto way to store any metadata for a long time. And it's all about the metadata. So Parquet is another columnar format, but it's based around the idea that your columns can be stored differently, they can be compressed differently, and they can do all kinds of fun things. They are append only. You can only add to the columns, which is fair, because when you start modifying them, all the interesting metadata starts breaking. So things like, you can store things like the length of the column, the highest number, the lowest numbers, and all this stuff. And it's designed around the idea that you're going to be using this for efficient lookup and also basically the OLAP side of data. These are not really used as streaming data formats. These are where streaming data nearly always ends up. So what you end up with is that you end up with the idea of a file format which can do all kinds of fun things. Like in recent times, bloom filters were added, and bloom filters are a way of rapidly checking if data either does exist, is either not there or might be there. It's a probabilistic data structure for rapid lookup. It's the reason things like RocksDB is fast and Cassandra is fast when it comes to lookups, is using bloom filters to exclude vast quantity of data. You can also do some fun magical compression per column. So Snappy works really well for some. Run length encoding is kind of magic for others. So if you have a couple of columns where the data only changes by a very small amount, but then it stays the same for a long time, like we have long runs of yeses and nos, binary data like that. If you run length encode it, you can often compress that down to a rather crazy degree. And Parquet is deliberately built with this kind of stuff in mind. So a bit dishonorable mention or honorable mention is thrift. Now, thrift came out of a lot of thinking around exactly the same kind of mindset, designed to be a kind of better XML. And like a lot of these other formats I've mentioned, it even came with its own RPC format. So Hive and others came originally with a kind of thrift protocol. The original Cassandra way to access it was via thrift, and you just RPC'd through it. Both Apache, Avro, and Protobufs, of course, with gRPC, are often used heavily in conjunction with heavily as an RPC format. Thrift kind of survived longer as an RPC format than it did anything else. But these days, outside of a few organizations, and bizarrely TikTok being the biggest one I can think of, thrift is sort of gone out of fashion. Is that a good thing? I think so, because of the fewer of these formats, the better. It just means there's less wire formats to contend with. So let's talk about a bit of where it all started. Now, a lot of this stuff started in the Hadoop era. And if you're looking at Google, the MapReduce era. So Hadoop kind of a bit like Parquet and others came from the idea of, hey, those guys at Google have done something very cool. And the MapReduce paper was a huge deal, as was the Dremel paper. And the idea was, how do we make these things appear in the open? And like a lot of these good ideas, they kind of spread. And over time, Parquet became the basis of all these different tools, from Hive Hive evolved into Iceberg, evolved in and Hoodie, and also then and Paimon came later to kind of bring this idea of that Parquet files are a really good way to store long-term data. Now, I wrote this slightly before the Duck Lake thing happened, but even there, it shows that some of the best database researchers in the world said, still, Parquet, good mix. And with tools like data fusion coming along in Rust, Parquet is increasingly the de facto way to store data for long-term usage in both object storage and on disk. Now, Kafka and Pulsar basically also picked up Avro initially as their kind of lingua franca, and a lot of the tools that came with them, from KSQL and to Flink, use Avro as kind of an internal tool because it's very easy to use. It kind of fits that kind of mentality of row-based processing. Interiors of these things are a bit different. But hey, that's where we started out. Now, we're always going to ask about what's new. Now, this is going to be no surprise to some of the people who watched one of the talks this morning. Let's talk a bit about Apache Arrow. Now, Apache Arrow is a column-based in-memory and IPC format. So IPC is intra-process communication. It also does RPCs because everything does RPCs, because that makes sense these days. Now, most of the things we've talked about so far have been row-oriented structures, where there's some metadata defining where each of the fields in the row start and stop. Like the byte offsets are equivalent, or in the case of protos, they don't exist, which is why protos are so small. But also then you have a bunch of extra fields there about versioning. Avro contains metadata so you can read the whole chunk. Whereas with Parquet and therefore Avro, Parquet and therefore Arrow, we have a big chunk of metadata at the top telling us what columns are what and how long they are. Now, this is important because of why, when you start looking back to how CPUs work, because it's all about the metadata. Now, the big point about this is that you generally don't want to do different things on a CPU. A lot of us have heard of what's known as memory starvation. So this is when your data cache is not aligned. So in general, you always want to be reading things in a long string of data. This is kind of why Kafka was originally very fast was the ability to do the same thing and load data in a long thin stream and serve it over the wire. CPUs are the same, and memory is exactly the same again, which is to load data off disk into memory and then off memory into your CPU cache. You want to use something called the prefetcher and make it happy by reading data in a long line. So if your data is a column, you're scanning through it, that's very good for prefetching and for cache alignment. But then the other half of your CPU is the instruction cache. And this is the bit that's often neglected, where it makes a huge difference to be able to do the same operation over and over and over again before you change. So let's say you're trying to do some filtering on a record, right? And you want to filter, by X, Y, and Z. So when you're doing your X filters, rather than going X filter, Y filter, Z filter, though that's very good for, data cache alignment, you just read 1, 1, 1, 1, 1, 1. It's really bad for instructions because you have to do a different check each time and your branch predictor is going to go all over the place. Instead, if I check all my X's in a row, then all my Y's in a row, then all my Z's in a row, I can gain a quite significant speed up because if I ever run out of instruction cache, I stop. If my data cache runs out, it's a bit different because I just have to wait till it fills. But if I were kind of if my instructions have to hop around, I might lose my data cache anyway, because it can only be held for so long. Now, this really makes Arrow that kind of big forward-thinking piece when it comes to a lot of computational engines. Back to data fusion in Rust, this is the idea that all in-memory operations in data fusion are done as Apache Arrow. If you look at the famous math library NumPy, increasingly that's moving into being pandas. So it's a NumPy. That was originally what pandas was based on, pandas being the data frame library. But now pandas is moving into Arrow for one, performance, two, standardization. Now, the Arrow project is all about computation and loading things in and out. So the big upgrade for pandas here has been that by moving to Arrow, one, it speaks the new kind of format everyone's trying to use for their in-memory computation. And two, it's nothing magic anymore because NumPy is full of a lot of magic. Also, as you kind of continue down this road, you suddenly realize that a lot of databases are increasingly speaking something called the ADBC protocol. Because if JDBC was fun for Java, but the ADBC is the idea of saying, I want to pull columns at my database rather than rows, because more often than not, I might just want to do a select field, and then pull both those columns out. Now, if both my database and most analytical databases are all column-based anyway, and my reading system is in a column as well, it makes sense that I should actually do columnar access. So Apache Arrow works really well here. Now, once again, if you remember from your talk this morning, something called Flus happened recently. Now, Flus is the unified Flink streaming storage engine. Now, this is a columnar streaming engine. I'm not going to go into too much detail because Jack Wu did a wonderful talk on it, which I believe was today. If not, it's tomorrow. Please enjoy. And I want to kind of like highlight two very specific things, which is that most of the streaming systems we have already, particularly in the case of Kafka, a bit less so in Pulsar's case, but both of those systems are designed around the idea of throwing rows around because an event appears complete as a row. Because if I have the state of a sensor, I'll have its temperature, I'll have its battery life, and I'll have its location. Brilliant, that's one row, and that's a logical unit of an event. However, event streaming systems aren't the same as analytical streaming systems. They serve different purposes. And more often than not, I don't need the whole event when I'm doing analysis, but I still want to be able to stream. Now, Flus basically kind of lives on the idea that with tools like Pymon and Iceberg basically giving you this kind of effectively a big pile of Parquet files to back onto, what happens if you put a kind of almost in-mem layer over the top, a mem table to your SS tables, if you will. And this is where you come down to the idea of saying, if I stream around in Arrow, I can then do a columnar query through my streaming layer and have always up-to-date data at any given point in time. And what this means is that you can do things like predicate pushdown into your actual streaming layer. Because a lot of the times, particularly with Flink jobs, where you're doing lots of multi-step processing, you really do not want to deserialize things over and over again. You just want the data as is. And more importantly, you don't want to pull all the irrelevant fields. So if you imagine you've got a kind of a wide table effect, And you really only want the ID of the user, their name, their bank balance. You do not need to know their current location. You're maybe not even allowed to have their full name due to a GDPR type scenario. You only want to query that small amount out. And then once that's into your thing, you're pulling a hell of a lot less data over the network. Now, if you remember back to the early slides, data is slow, particularly over networks, and networks are not cheap. A lot of what we do these kind of things for is because of performance, and performance is directly applicable to cost. If it's fast, we don't do very often, it's cheap. Fast is the easiest way to make things cheap in computation. So Fluss gives you the opportunity to do this kind of predicate pushdown streaming, where you have an analytical layer which goes all the way into your into your data lake, giving that full stream house capabilities, meaning that you can then say, I want to pull data with types out of my streaming system and have all the way through. Now, a little bit of a call to action because of we need contributors for Fluss. It's cool. I'm sure Jack did this earlier. It's all open source, and we're offering all kinds of fun things around the outside. And it should be in the Apache Foundation shortly. But the key thing to know with all of these different formats, and I want to kind of really hit this home, is that you will choose the one that matters for you. Please don't use protobufs. It is a trap when it comes to actually performance down the line. Avro is still a gold standard for a reason, but increasingly Avro starts to look shiny, but only really makes sense if you do actually have the ability to use the predicate pushdown. Otherwise, you're basically paying for an optimization you're not using. If you're pulling very large quantities of data around, Avro makes more sense. Now, from my game dev days, I am happy to tell you of all of the wacky wild ones we had out there. Now, flat buffers are excellent if you need something like more than a protobuf. They allow for you to read directly off the wire. Very powerful if deserialization is your biggest bottleneck. I always like message pack because it's completely JSON but binary. It's like Bison except slightly less MongoDB flavored. And then I'm going to do one big shout out because contractual obligations say Flink Forward is in Barcelona this year, and we'd love you to come along. Now, to try and say the next thing here is that, so this is our big event about Flink. We work closely with people like Stream Native around this because fundamentally, like, open tech is for everyone, and we want everyone to come along and kind of learn about what we do and see what we do with others. Also, this is me. I'm on LinkedIn. I talk too much, but I also write too much. So if you care to see even more of what I do and what I witter on about, come find me on LinkedIn. Thank you very much for listening. If there are any questions, happy to answer them.
Yes, it has been kind of over time. But I really love this talk. It's because I think Ben always give a really great story about the entire history of the format evolution. While I think waiting for some of the Q&A pop up, I do have one question for Ben. I think you talk about the entire history moving from row format always all the way to the Apache Arrow and also the Bruce project. To I think the reason we kind of talking about here is to kind of maximize the efficiency that we get out of the CPU cycle and as well as the network bandwidth. But in the other context, is the now everyone is talking about AI and everyone is talking about an agent to a certain extent. And what large language model is really good is about text, and what is really good is about JSON format. And what's your opinion about the entire stream processing, data processing, moving all the way to Parquet era, and while large language model is still JSON? And how do you feel this entire two worlds get together?
It's this wonderful loop, right? It feels like we've gone all the way back to those pure text processing libraries again from the yesteryear. I think it's called like Snowball and things like Tickle were pure text processing. And it feels like we've gone all the way back to kind of like early days of Unix systems thinking again, where everything is text, everything's a pipe. And yes, JSON works very well with large language models. Bizarrely enough, in my experience, when you start using large language models with their structural responses, you don't actually want to give them a schema because they do not understand schemas. right? They're
Exactly.
bizarrely bad at schemas. Like tell them to fill a JSON and give them the schema as part of the actual bundle. It tends to work a lot better. But this is where I come back to message pack, particularly as kind of like my dark horse choice, which is it's JSON, except it's binary where it can be. So at least over the wire, it's really lightweight and it has the fastest serialization, deserialization I know of. So I don't particularly like, I find MCP type things to be they're a really great idea in principle, but due to their very JSON nature and the fact that like you
Yeah.
fundamentally are now throwing even more JSON around your internal network, I'm always of the opinion like, couldn't we have chosen something a little better?
Probably a question to Anthropic and also the entire MCP community. Maybe adopt something more structured from there.
I get the
Like
impression maybe
Arrow. Yeah.
I just hear the cloud vendors cheering to the bank, going, "Yeah, as if our bandwidth got slowed."
Cool. I know the other three session already get started, and people probably want head to the other sessions. But I don't see a new question coming up. But if you do have any questions, you can connect with Ben. Ben always give very insight views in anything. I would say, not just about data streaming, stream processing, anything regarding to tag. I think if you talk to Ben, Ben will give you very insight thoughts there. So go connect with Ben and thank Ben for jumping in. Really great to have you here. Thank you.
Cool. Yeah. Last one, there's a question about Parquet. And the answer is yes. High frequency logging does work great in Parquet. The lack of a variant type is a problem at times. So really for logging, you want variants, which is why most logging databases do not use Parquet behind the scenes.
Yeah, I missed that question. Thank you, Ben.
Sorry, don't worry. I finally found the chat window. I lost it earlier.
Yes, cool. Hope that answered your question. And if you have further questions, let's connect with Ben offline. And great to kind of have you here, Ben.
Well, thank
Thank
you so
you.
much for having me. Bye for now.
Bye bye.